Hello and welcome. In this video, I'll be covering section 6.4, which is over radians, arc length, and angular speed, as well as linear speed, technically. After this video, my hope is that you'll be able to find points on a unit circle that are determined by real numbers, to be able to convert between radian and degree measurements, also finding coterminal, complementary, and supplementary angles, to be able to find the length of an arc, or to be able to find the measurement of a central angle if you know the length of an arc, and also being able to convert between linear and angular speeds. Now, the first thing in this section we're going to talk about is how we can measure angles in slightly different units than what we've so far been doing in class. So thus far, every angle we've been dealing with has been in degrees for the most part. So what we are now going to introduce is a new unit of measurement called a radian. In order to do so, what we need to consider here is if we had an angle drawn, say, on a coordinate plane, let's just maybe picture a circle with a radius of 1. Technically, I can do this with any size circle, but probably easiest to just kind of picture if I had a radius of 1. That specific circle is called a unit circle, which we'll explore a little bit further later on in this video. But a unit circle, again, centered at the origin with the radius of 1, would create this equation here you can see in the middle, x squared plus y squared equals 1, or would be the result of that. And so what a radian really is if I take whatever the radius is, which as we're seeing on the picture here at the bottom, if I had a radius of 1, essentially if I were to then utilize an arc length that's the exact same amount, so in this case having an arc length that would be equivalent to it, so it'd kind of be like if you could picture taking this amount, whatever that radius is, and being able to fold it along the circle itself as it's kind of being drawn there. I'll go ahead and get rid of that so it's not as busy. But whatever that creates, in this case it would create this angle here at the beginning, that's considered 1 radian, or that would be the equivalent of 1 radian. And as I mentioned before, it doesn't have to be this unit circle. It could actually be a significantly larger circle. We could have a radius of 25 for all it matters. And ultimately what we would do is just measure whatever arc length is also 25, and it would create this exact same size angle that you can see off to the side. So if we had to compare like what 1 degree is in comparison to 1 radian, 1 degree, as you can see right here, that's significantly small, right? It's almost like it's the same 2 rays on top of each other, just with a little bit of space in between to create that angle. Whereas 1 radian actually is a fairly large amount. As you can see here, it's approximately equal to 57.3 degrees. So again, just to kind of give you an idea of what a radian is, where it comes from, that is essentially the way that we would do it. And technically, if you didn't believe it, you could try and grab a compass, make any sort of circle. Basically, from there, maybe take like a piece of string, since you could bend, you could actually bend that. Cut it to whatever that radius was that you just did, draw it along the edge of the circle, and you'd notice it would create an angle that's pretty much the same size as what's on here. There might be a little bit of margin of error because you're utilizing something that's not perfect, but you should hopefully convince yourself, no matter if it was a really, really tiny circle with like a radius of maybe like a centimeter, or if you had a really giant circle, something that was maybe like 100 meters, right? Essentially, if somehow, some way you were able to measure along the curved edge the same amount as what the radius is, it creates that angle 1 radian, which is again approximately 57.3 degrees. So with that now being presented, let's go ahead and discuss some of the common angles, some of the, I guess, more easy ones to think about. If we think about going, let's go with the far right one. That's probably the easiest one to picture. So if I think of all the way around being 360 degrees, what we're also going to be able to call that is 2 pi radians. And if you think back to maybe like a circumference of a circle formula, this will make a little bit more sense why it works this way, but 2 pi times r would be that amount. And it happens to be the same as like what 1 revolution is. So as we can see here, 1 revolution is either something we can continue or consider to be 360 degrees, or we can consider it to be 2 pi. Doesn't really matter which one. It's just more of a matter of what unit do I want to be in. For most of the formulas we'll have for the rest of this section, we'll want everything to be in radians. So if you did have the option to choose for the specific formulas we'll talk about here in a second, we'll want to choose the 2 pi as that revolution. Now, as far as other possible angles that we could have, if we think about If 2 pi is all the way around, hopefully it's not too unreasonable that halfway around right here, this 180, that's going to be just pi radians. And we could go even further down. We could go, well, half of 180 is 90, so half of pi, that would be pi half. So notice we've got these connections that we can use to our advantage. Really the one that we're going to focus our attention on, if I try and like make it obvious here, is going to be this one right here, where we'll actually take advantage of the fact that 180 degrees and pi are equivalent to one another. Technically, every other ratio would also work, but that's the only one that technically wouldn't need to either eliminate a fraction within or would need to be reduced if it came down to it. So what we're going to take advantage of when it comes to converting is either we'll be able to say that there's 180 degrees per 1 pi, or we might end up using there's 1 pi radian per every 180 degrees. If I were to use one like this last one, let's say I just chose one of those, it'd be 360 degrees per every 2 pi, which technically is true, but the 360 and the 2 can technically reduce, and notice it would turn right into one of these two versions. In this case, it would actually turn into the first version if I actually drew over to it correctly. So again, that's really the ratio we're going to talk about. That's really what we're going to take advantage of. And if I go ahead and just scroll ahead here, we've got our conversions here. So if I ever needed to convert, if we go just one at a time here, from degrees into radians, the easiest way to think of it is, okay, we know 180 and pi are equivalent to one another. So I just need to think what unit needs to cancel. So if I'm trying to get out of degrees and turn it into radians, that basically means I need to have a degree unit on the bottom. So I would put 180 degrees in the denominator, which then means pi must be in the numerator. And if I go ahead and multiply the angle, the degree unit would cancel, leaving me the radian unit. Now let's say I wanted to go the other direction. Let's say I was actually starting in radians and I wanted to convert it into degrees. At that point, that means I want to cancel the radian unit, hence why I would actually put pi, and technically I could say radians if I need to, but it's actually implied if you don't see a unit right there that it would be in radian format. So I should actually have a degree unit on that 180. My apologies for that. So anyway, if I remember those two ratios, I should just be able to multiply whatever angle I have, cancel the corresponding unit that I want to get out of, and then it would leave whatever the other unit was. So hopefully this won't be too tough when we work through an example. And let's go ahead and give one of these a whirl. So the first example we got here is I want to convert from degrees into radians. So to start, that just tells me, okay, I need to cancel that degree unit. So that means degrees need to be in the bottom, or the denominator of whatever I'm multiplying by. So 180 degrees on the bottom, which means pi radians is on top. And ultimately what we would do is just take the two numbers, in this case it would be the 120 and the 180, and just find a way to see if they can reduce, which obviously that should be able to happen. Fortunately for us, if it's something that you don't want to have to spend a lot of time on, we have access to the TI-84s that can do that reducing for us. So let's go ahead and bring up a calculator and show how that would work. I would ultimately bring up that fraction template, so alpha y equals in the first option, type in whatever the numerator was supposed to be, so 120, on the bottom have 180, press enter, and notice it just takes us straight to that reduced version, 2/3. Now why didn't I type in pi? Well, ultimately I want to have my answer in terms of pi, so we can just kind of take note of, okay, I know the numerator will have pi, let's just simplify the numbers, so this actually would turn into 2, notice pi staying on top with that 2, and then I have 3 on the bottom. Now I don't have to write radians if we don't necessarily want to, because the implied thing is if you don't see a degree mark, then that means it must be radians. But if you wanted to write radians, there's nothing wrong with it. Like as you can see with example 2, I wrote radians after each one of those, but that was just more for the notes to be clear on like this specifically is radians. But again, mathematicians kind of have taken this to be if you don't see a degree marking, then that implies it must be in radians. Now if we go ahead and try the next one where it's not as nice of a number, we can technically do the exact same thing. Even though this has a negative in front, that just is going to tell me it's going to stay negative. But just like before, I know I need to cancel the degree unit, so 180 is going to be in the bottom, and then we can go ahead and try and simplify that. So let's see how easy this one turns into if I do the alpha y equals. It might actually just give me whatever the decimals are. So what was that number? 297.25, sorry. 7.25 on top. On bottom I know it's going to be 180. Let's see what happens. Yeah, so it did turn it into a decimal. However, that's not that big of a deal. What we can do is just see if it converts nicely into a fraction. And all I have to do is press math. First option there is convert to a fraction. And if I press enter on that, notice it turns it into 1,189 over 720. So if I go ahead and switch back there, 1,189 over 720. And I have pi in the numerator, and you can't forget about this negative sign, so it would just have a negative in front of it. And voila, we've got it converted. Or if you wanted to, we could, for something that started in a decimal format, I'd actually approve of that unless it's stated otherwise. You could probably go ahead and type that in as that decimal we got before, which was the 1.651-ish. So approximately 1.651 would be a decent way to round that one. Now, as far as going the other direction, as example 2 here has us going, now I want to get out of the radian unit and convert it into degrees. So that means I actually want the radians to be in the denominator and the degrees to be in the numerator. So notice I'm just basically taking that same ratio but flipping it. And now when I multiply, what's kind of nice here is this one actually had pi to start, so I can go ahead and say, well, that pi will cancel with that pi. So really this is just turned into what's 3/4 times 180. So again, we can bring the calculator back in. We can just type in 3 divided by 4 times 180, and it gives us our answer of 135. Or we could also use that fraction template. So just to model it that way, we can go 3 on top, 4 on bottom, and then times 180 off to the side, and notice it gives us the same answer. So whichever way you want to type it in, using the divide or using the fraction, it gives us the same result. So this would convert to, as we just found out, approximately, actually not approximately, that was exactly 135 degrees. Okay, as far as the next one, notice it doesn't have pi, so this one won't be as nice, meaning it's going to have pi in the denominator. So I could just try and figure out what's 8.5 times 180. So let's do that really quick. 8.5 times 180. And I get 1530. So this would be equivalent to 1530 over pi. Or we can go, since it did start in decimal form, we could go ahead and divide by pi. So if I did that really quick, I'll just divide that answer by, and pi, as you can see here, is right above the power button. So it's going to be the second of that power button to get that on the screen, and it gives me that it's approximately 487.01. So let's just call that 487. Again, I'm putting intentionally the degree unit on there just to make sure that it's relatively obvious. I didn't do that here, dang it. So this would be in degrees, yes. But as far as the final answer, I'd say probably on a test I would want it to just be that 487. Having pi in the denominator is just kind of a weird appearance, I think you would all agree. So converting it into that decimal form for that one that didn't start with a pi kind of makes sense. As we can see here at the bottom, I've already mentioned this a few times, but if you don't see a degree sign, that just means it would be implied to be in radians. But if it's something that has been provided, you don't necessarily have to write radians the rest of the problem. All right, let's move on to the next topic, which is arc length as well as central angles. So arc length and central angles are going to be connected to one another. The book you guys use often represents the arc length using this letter S. I think that's mainly just because it's the arc is subtended by the central angle, or the central angle subtends the arc length. With this one, it would just be whatever the S value is, that's just going to be what we call, let's go ahead and use a different color here, this is the arc length. So that relationship, if we think about like circumference of a circle, is just 2 pi times r. However, if my angle on the inside was a little bit smaller, it happens to just work out that the arc length is equivalent to whatever the radius of the circle is times whatever the angle is. So I'll just use theta to represent that. And that color is not the best, so I'm going to go ahead and just rewrite that. But technically it's typed up on the next slide. So S equaling r times theta technically is what we had. So if it was all the way around, which is 2 pi, notice that again is why the circumference, the all the way around, would just be 2 pi as the theta times the r of whatever that circle is. So here it's just kind of showing like if I had a radius 1, or if I had a different radius r, as that r grows, the arc length naturally should grow, or as that radius is getting smaller, that would make the arc length get smaller. It does not really change at all. As you can see, the arc length, or sorry, not the arc length, but the central angle itself would not really change. It would just change how far along the circle it might be going based on how long or how far out it happens to be from that center. Oops, a little too far. So that radian measurement, as I kind of mentioned here, we've got three different versions of that one. The one I just presented there was the arc length S is equivalent to R times theta. What is key with this is that theta does need to be in radians. So I did fail to mention that on the previous slide there, but it does need to be in radians for this formula to work. So if it wasn't, as I'm seeing this on the screen, I should have looked right there. It must be in radians, as it said. But for this one, technically we can have different versions of it. We could isolate the theta. So if I did isolate the theta, notice it creates this other version right here, because all I would have to do is divide the r over. So the theta really is equivalent to the arc length divided by its radius. Or we can do yet another version where I could get r by itself and divide the theta over. So I also could solve for the radius. So there's kind of three different main versions, and it just kind of depends on what the question may want as to which of those three is the most useful. I think the one that's in the middle, the S equals R times theta, just because it doesn't have a fraction, is probably the easiest to quote-unquote memorize, and then just realize from there all you'd have to do is manipulate by moving things from one side to the other, by either dividing the R or by dividing the theta, and it would isolate one of the other variables. So that's the one I would say probably is the most useful from this, but if you wanted to try and memorize all three, have at it. But again, this is just something where the radian measure for that middle or central angle happens to be the ratio of the distance traveled from the radius or with the radius for that specific thing. And that creates the arc length formula that we just talked about not too long, but again, key part of this is the angle does need to be specifically in radians. All right, so let's go ahead and try out a few examples that utilize that. So if I maybe just near the top, kind of remind us what some of the formulas are. The main one is that the arc length would equal the radius times the central angle, again, specifically where the central angle is in radians. So here it says find the measure of a rotation in radians when the point is 2 meters from the center. So that to me sounds like it's a radius of rotation, and it's traveled 4 meters. So that's like the arc length, or that's the S. So here it would be, if I wanted to, it would be 4 is equivalent to the 2 times theta, and then solve for theta. So for this one, it would just be divide the 2 over, and I'd end up getting 2, and then the unit here would be radians as my theta, or my central angle for that specific scenario. As far as the next one is concerned, find the length of an arc for the circle. So it sounds like I need to solve for S this time. It gives us that the radius is 5, so there's an R value with a central angle of pi thirds, so that's a theta value. So here it would just be S is equivalent to the R I was given, which is 5. I'll go ahead and use these units centimeters, times the angle in radians, so pi thirds. That's nice, it was already in radians. Had that been in degrees, I would have needed to convert it first, and then now it's just a matter of simplifying. So here it would be the arc length is equivalent to, it looks like 5 pi thirds, and then that unit of centimeters would still be there because an arc length is technically a distance. So since it did give us a unit of measurement, try and remember to include that on your final answer. Now on to the next topic in this section, which is angular and linear speed. So key part of this is that word speed. Hopefully has already been stored in your heads as something that's per unit time. So probably the speed that you recognize most would be something like a distance traveled per unit time. And what we actually would call that is actually linear speed. So linear speed is more of a distance traveled. And then the units of time can be anything from seconds to minutes to hours and so on and so forth. It would just be something where pay attention to what the question may want. And if you need to convert, say, minutes into seconds or maybe minutes into hours, just realize that we can do that utilizing some older strategies we've hopefully collected along the way. Angular speed for sure is probably something that's new, but angular speed is something that could be either in like a degree or it could be in a radian, but ultimately it is just a how much is the angle changing, specifically the central angle, how much is it changing per, and then unit of time also could still be seconds, minutes, hours, doesn't matter. Your book introduces the Greek letter omega, which is kind of like a W looking thing. So it's a lowercase omega is technically the name of it. Why they use that, I'm not really 100% sure, but when you see that, just realize that's what it's trying to have you reference, is that's representing the angular speed for this. And as you can see, it would just be whatever the angle is traveled per, and then this is just a unit time. So it could be degrees per something, like minute, could be radians per minute. And again, like I mentioned a few times here, it's the time unit can be really any of the options that we got. Seconds, minutes, and hours are the most common. Linear speed, on the other hand, is more of a how far I've traveled, so that's more where that arc length concept we just talked about gets involved. So it could be like the arc length per unit time, as this first version is, or since arc length is equivalent to r times theta, we could also have it be like r times theta divided by t. And since we just introduced that omega was technically theta divided by time, we could separate that and just say, well, that's the same as r times omega. So there are 3 different versions. All really are saying the same thing. It's just a matter of maybe what's been provided for you. Do you know the arc length? Do you just know an angle and a radius? Or do you know an angular speed and a radius? And regardless of what's going on there, we can technically come up with that linear speed, which oftentimes the letter V kind of for velocity will get somewhat thrown in there from time to time, but doesn't necessarily have to be V. It's just your book will often use that as well. So hopefully this is all kind of making sense. Everything is just a per unit time for that speed concept. And we'll go ahead and work through a few examples here, hopefully to solidify that. So one example that could hopefully solidify this is the situation where we've got a satellite in orbit. So that would be 1,200 kilometers above surface level. And it says that it's completing a revolution every 90 minutes. So it's trying to have us figure out what is the linear speed of that. And if it's given in kilometers and the other one is in minutes, it may as well be something we answered in kilometers per minute because it doesn't state otherwise. Now, since that's just 1,200 above surface level, we technically need to go all the way to the center. So that having the extra little caveat here of there's also a radius for the Earth that will just approximate as 6,400 kilometers. Ultimately, what I need to do is figure out how far is that satellite actually from center. So that really would be, for my radius in this case, the 6,400 added with the extra 1,200 it is above surface level. So that really gives us a total of 7,600 kilometers for our radius. So this wants us again to figure out our linear speed. So it seems to me like if I've got my radius, I need to figure out how much is the angle that's changing. So this is where that keyword revolution, we need to either think 360 or 2 pi. But for this one, let's go ahead for arc length that needs to be in radians. Let's just use the 2 pi as that. And if it's every single 90 minutes, that would be technically my omega being 2 pi per 90, which I could reduce to pi per 45. Just by dividing each of those by 2. So to come up with what my actual linear velocity is, I'll go ahead and change color here really quick. My linear velocity would be whatever that radius is, 7,600 times pi divided by 45, and this would be in kilometers per minute, since those are the given units. So if we go ahead and maybe try and see if that simplifies, 7,600 divided by 45, let's just see if that turns into a nice fraction. I guess I could have used the fraction template, but 1520 over 9, and then that would be just times pi. So 15, hopefully I typed that in right. Yep, so 1520 over 9. Kilometers per minute, or if we wanted to actually just figure out what this is in decimal form, we can go back and just do times pi and see what that turns into. So about 530 point, let's just call that 6. 530.6 kilometers per minute. So that thing up there, it would be cruising, but if it's going all the way around in 90 minutes, that should kind of make sense that it's cruising pretty darn fast up there. But if we needed to have maybe a different example, let's say maybe it didn't use the word revolution, sometimes it might use rotation, That would be still the same general concept. I would just figure out what is that as an angle, either 360 or 2 pi. 2 pi is usually the one that makes the most sense, especially for something that's talking about speed. The other option, maybe this could be presented as if it gave me something in degrees, immediately convert it into radians. So perhaps maybe this is better to just do another example in class if you need one. So just fire away with any questions if you do have any, and I'll be happy to work through it one-on-one with you if need be. Alright, so as I mentioned before, I do have a completely separate video that I'd actually recommend you probably watch that one instead, that I've grouped in near this, but the unit circle is the next concept that we're going to get into and kind of talk about how that can help us identify what sine, cosine, and tangent of specific angles that are kind of nice. So this is where that 30, 60, 90 triangle and 45, 45, 90 triangle would get involved. So if we just do a quick little recap of how that would work, this would be based on how it's been drawn, that would be like my 30-degree angle down here. This would be my 60-degree up here, which then makes the 90 happen to be in this bottom right. And if you recall, the way that we labeled this would have been normally like a 1, a 2 for the hypotenuse, since it's double the short leg, and then the longer leg is just whatever the short leg is times the square root of 3. However, if I want it to be the unit circle, what I'll want is for that diagonal one to actually be like the radius. That way, like when I draw my angles out, I can then picture like whatever my triangle is with the x-axis, if I were to maybe include the axes here as well, where my 90-degree angle always hits that x-axis like we stressed hopefully in the last class. And in this case, notice that hypotenuse is, with it being a 2, I would technically want to scale it down. So the way that we can do that is just dividing every side by 2. And if I now go ahead and replace each with their value, I'd end up with 2 divided by 2. That actually turns that into a radius of 1. And then the other two sides can't really reduce at all. I've got 1/2, and then rad 3 over 2 is the options there. Now looking at a 45, 45, 90 triangle, or at least reviewing that, if those two angles are the same, the two legs would also be the same. I don't know why I wrote it that way, sorry about that. And my 90-degree angle down in the bottom right. But this one normally we labeled as like 1, 1, and then square root of 2. So if I wanted to try and force that hypotenuse, just like I did before, to be 1, I would just divide everything by square root of 2, and then try and simplify it to the best of my ability. So the hypotenuse now, by doing that, I can go ahead and cancel and turn into a 1. 1 over a square root of 2 I would want to rationalize, so multiplying top and bottom by square root of 2 over another square root of 2, such as this. That would just turn into a square root of 2 over a regular 2. So I'm going to go ahead and just get rid of all that monkey business there and just call that square root of 2 over a 2. And the other one obviously would do the exact same thing since it was the exact same ratio. So as you can see here, our options now for these side lengths turn into 1/2 is like the smallest option. Technically rad 2 over 2 would be the next largest option, and then rad 3 over 2 would be the next one after that. And why that's going to be important is if we think about on the unit circle, or if I had a circle that was where the origin maybe was where the angle was out on the circle itself, I would have an ordered pair that I could probably figure out because I have now the horizontal distance. So in this case, this would be like square root of 3 over 2 for this example if I was using this as the origin over on the far left. And then on the y value, it would be the vertical distance, which would be like 1/2. Doing that kind of same concept over here with the other one, if I said, okay, here's my center, probably should say that if this was on a coordinate plane. It's kind of hard to maybe visualize that because I don't have a grid in the background, but if I then said, what's this point out here, I technically could say the x value would be a square root of 2 over 2, and then the y value also would be a square root of 2 over 2. But again, key idea here is just paying attention to those three ratios are going to be very repetitive when it comes to what's coming up next, which is the unit circle. So I'm going to go ahead and just scroll ahead really quick. This is what it would look like. In class you should have gotten this, or if you haven't gotten one already, I can get you one obviously. But this is as far as like being able to fill things in, this is what we would go through and do. So again, I don't know if I'll end up spending a lot of time talking about the how to fill this in this video, since I already have a separate one that's gone a little bit more in depth than I currently am. I'm kind of rushing through this. But ultimately what our goal would be is we'd start where 0 degrees is, so the positive side of the x-axis, which also happens to be 0 radians, And then what I could do is then just kind of fill out all of the degrees as I go around, utilizing the fact that I've got 30, 60, 90 triangles, which I'll go ahead and sketch what one of those would look like. This would be one of the 30, 60, 90 triangles right there. I've got another 30, 60, 90 triangle right here. And then I have the 45, 45, 90 triangle, which is the one in the middle. So if I kind of take advantage of what we could do there, we could just count by 30s all the way around, skipping the middle ones, so 30, 60, then 90, then 120, and so on and so forth. Hopefully that wouldn't be too tough to be able to accomplish on your own. After all, this is something, the expectation moving forward will be that we can actually kind of recite this from memory. So this would just be one possible pattern that you could take advantage of that gets majority of the degrees filled in. It just kind of skips the ones in the middle. What is kind of nice is if this is 30 degrees, that angle in the middle is exactly half as much. So I could just go, well, half of 30 is 15, and just add 15 to whatever the one is before, or take away 15 from whatever one was after. So if we maybe continue doing that just to fill in the rest of them, 120 plus 15 would give me 135. 210 plus 15 would give me 225. And let's see, 300 plus 15 would be 315. So at least gets me all my degree markings on this specific thing. Now again, this is called the unit circle because it's a radius 1. So we could take advantage of knowing this distance here being 1 should allow me on each of the axes to know that that must be 1, 0 because it's to the right. That means the one at the top here must be 0, 1 because I'm going up. And then once I go into other places as I go around, say like for 180, for example, that's actually going to the left, so that actually gives me some negative values. Same thing going down to this bottom angle, that would be 0 now with -1. And as mentioned just a second ago, like my ratios that are going to go in each of the ordered pairs in each of the quadrants will just either be a 1/2, a rad 2/2, or a rad 3/2. So as far as a pattern that we could do is we know that all of those are over 2, so I can just go ahead and take advantage of, well, the side lengths are all going to be over a 2 because I've scaled those triangles to where the hypotenuse was a 1, and it created 2's in denominators. And at this point it would just be, let's think of what's happening with the x's. Well, as I go around the circle like this, the x values actually should be going from 1 towards 0, so that would actually make it decrease. So if we think in terms of our options from greatest to least, that would go square root of 3 first, square root of 2 second, and then technically square root of 1 I could say, but square root of 1 simplifies, so that would just be a 1 in that spot. The y's on the other hand actually go the other way. They start at 0 going towards 1, so they actually increase. So it would go from a 1 to a square root of 2 to a square root of 3, and notice we've now got the ordered pairs at the end of those filled out. I'm not going to continue through all of the quadrants. I just wanted to at least kind of show some of the patterns. Again, this is more for another video, but when it comes down to it, if I needed to fill out, say, these points over here, I would just reflect them across. So it would be like this point, I could just say, well, it's going to be the same there, except now my x value must be negative because I'm on the left of the y-axis. Anywho, if we go ahead and maybe fill out some of the other parts here in the first quadrant, if we look in terms of like, if we know that pi is all the way around, or sorry, not pi, but 2 pi is all the way around. Sorry about that marking there. So if 2 pi was all the way around, just like 360, we could say halfway around is pi, which again, notice that connection of pi with 180 is happening there. Half of that up here must be half of pi, so pi over 2. And then I technically could just keep cutting in half for 45 and just call that pi fourths. But ultimately what I wanted to kind of point out here is if I know that this part right here, this is half of the circle, so that's pi. Notice if we look at those smaller pieces like this and just kind of total up, well, how much is each of those in relation to pi? Well, that would be 1. It takes 2, 3, 4, 5, 6 of those to get to pi. So basically that means one of those must be pi 6 or a sixth of pi. So if I get rid of all of that stuff that I just wrote, just to kind of show like the y pi 6 is going to be this first one. Hopefully that made sense. But I'd have pi 6 as what 30 degrees is. And ultimately from there I could just count by 6 from there. So this one would be 2 6, which reduces to a pi thirds. 3 6 would be the same as this pi halves that's up here at the top. 4 6, if I continue, that would be like 2 pi thirds, and so on and so forth. I'll just finish up at least like the top half here. So then one after that would be 5 pi 6, and then the ones in the middle are always going to be fourths. So if this was 1/4 there, that would be 2/4 there. So this one must be 3/4. And notice again, pattern-wise, they all have pi's in the numerator. And as we go, again, there's some other shortcuts we can work with, but the unit circle, ultimately what it helps us with is each of the x values are cosine values of that angle. All of the y values are sine values of that angle. So if I wanted to do, like, say, cosine of 30 degrees, I would just identify 30 degrees and then look at what is the x value, which in this case would be rad 3 over 2. So cosine of 30 is rad 3 over 2. If I wanted the y value, or sorry, the sine of an angle, I would just look at what the y value was. And then tangent, if you recall, is just a y divided by an x, which there's only so many options with that. What's nice and easy is the ones in the middle that have square root 2 over 2 involved. Them divided by themselves are either going to be a 1 or a negative 1. The other option I have is either rad 3 over 2 divided by 1/2, which gives us rad 3, or it would be its reciprocal 1 over rad 3, which if I rationalize would be rad 3 over 3. And as I mentioned in a prior class, we also have the ability to think of those as slopes, if that's helpful. So you could just think, what's the slope from the origin to that point? And that technically accomplishes the same thing. So like at 0 degrees, the slope there must be 0. And a vertical line slope, remember, would be undefined. Or you can keep falling back to, let's just do the y value divided by the x and use that. So anyway, I'm going to go ahead and just kind of end this video because this is probably already getting pretty long. And I do, like I said, have another video that explains a lot more in depth like how this continues. So I'll just leave this one unfinished. Go ahead and please watch that if you have any confusion, but if we did need to continue, it would just be starting to worry about some negative signs potentially as we go, and again, just continuing whatever patterns have been discussed thus far. Anyway, hopefully this video has been helpful. Sorry I'm kind of leaving this one hanging here, but again, we already have a different one that's probably a little bit more efficient in talking about the why all of that stuff works. And breaks it down even better than I did because I kind of rushed through that. But anyway, again, hopefully this video was helpful. If you have questions, please come find me, give me a chance to help. As always, I appreciate you taking the time watching the video, and we'll check you next time.